Thank you very much. I'm Renato from HHU in Düsseldorf. I'm presenting together with my colleague Benjamin today. So let's get started. So the problem we're working on is ontology construction. And as most goal-oriented dialog systems rely on an ontology, which is normally handcrafted so far. That's why we try to make this process more automatic and remove the need of human annotation. Another bad problem is when using pre-trained language models as a dialog system, that they do not generalize that well to unseen domains, which means that you need to construct maybe an ontology for the new domain and then annotate new dialogues for training for it to be able to be applied on the new domain. So we are focusing on the first step towards automatic ontology construction, which is dialog term extraction. So here we extract all the relevant terms. So basically slot value and domain candidates, which might be relevant for building an ontology. And then in subsequent steps, you might get the relations between slots and values, for example, and build the typical hierarchical structure of goal-oriented dialog system ontology. We're using this a simple biotagging scheme to extract the terms. And another thing is that in this first step, we focus on recall mainly because precision might be increased in subsequent steps. And also for dialog trackers, it's arguably more important to tag the relevant terms than not tagging the irrelevant ones. So now Ben will continue with our model structure.
Okay. Yeah, thanks a lot for the intro, Renato. So unfortunately, we are not there yet completely at an unsupervised term extraction approach. And so as a proof of concept of our new proposed method, we will try a transfer learning application where we train on a small data set that has very fine-grained annotations of these terms, and then see how well it generalizes to some unseen data set with way more domains and slot candidates. More specifically, so the seed data set that we train on is the MultiWOZ collection of dialogues. Those were dialogues based on booking some tourist-related entities, a hotel or a restaurant. And then we apply or evaluate our models on the schema-guided dialogue data set, which is way larger. So there's now an additional banking domain where you try to make wire transfers, and so on. So the main problem of our model will be just from this little data, try to learn how you can extract important concepts. And then we'd see how well it performs in this data set with 4 times as many slot candidates. So we claim that we propose completely new features for this term extraction task, both based on the internal workings of language models and then topological data analysis, a new branch of mathematical data studies, which allows you to find feature descriptions that have been invisible to classical linear or probabilistic methods. The baseline we are trying to beat is always the naive approach you might take in just fine-tuning a Roberta language model. So I talk you through our 3 different kinds of models. The baseline, it's just a Roberta model with a tagging head on top. Then, as I said, we look at the prediction certainty of a model in the hopes that this might distinguish terms from non-terms. And finally, we trained 3 different machine learning models on these topological features. And I'll tell you about this in a bit. Okay, so first the baseline. We took a pre-trained Roberta embedding, fine-tuned it on the term extraction task on the labeled MultiWOZ data set. And when we applied this to the larger SGD data, we observed 2 problems. One is this training needs a lot of data. So MultiWOZ is a small data set, and you could probably do way better if you had more fine-tuning data. And then these Roberta coordinates, or the features the model learned just based on the word embedding, they don't really generalize well to unseen data, because if you have a new domain, these words get embedded in a slightly different portion of space probably, and then the classification head just doesn't know what to do with this. So our first new proposal is the following. If we mask a word such as cheap in the sentence, I'm looking for a blank photo in the center, the language model will have trouble predicting this word in an MLM task, because there could as well have been the word expensive or moderately priced or whatever in there. So while if you mask a word such as the model will be very certain in predicting this word. So we compute these masked language modeling scores by going through the data set and just masking every word. And then on the basis of this model certainty, we train another transformer classifier on top. And this already showed better generalization capability. Our completely different new approach is now not just looking at single word vector embeddings in isolation from the Roberta model, but looking at entire neighborhoods in the word embedding space. For instance, given a word such as cheap, we took a pre-trained sentence word embedding and then looked at the 50 closest neighbors of this word. Our hope is that this point cloud captures different meanings of a word, and that on the basis of this, you will be able to build classifiers that are way more generalizable. And now the challenge is, how do you convert this point cloud into something that is feasible for a machine learning classifier? And this is my pitch for topological data analysis. So we were inspired by work that showed that singularities in this word embedding space could be used to measure polysemy of words, something that could also be related to the number of meanings. Okay, so my starting point is that topological data analysis, this can see properties of data sets that are completely invisible to whatever linear methods, probability analysis methods that you know of. For instance, let's say the neighborhood of this word sheep was shaped as in this cartoon picture, this oval collection of data points. Then let's say you run a principal component analysis on this. It's going to tell you that there are principal directions of most explained variants, but it will never be able to see that there's this hole or cavity in the data set, and that there's some non-trivial topology in this neighborhood. So there's a whole branch of math where you start from such point clouds and you build simplistic complexes, a certain generalization of graphs out of this data. So I won't go into details, but the advantages are this is very compatible with symmetries and invariant under perturbations or rotations of your data. If you just change the coordinates of a Roberta embedding slightly, any machine learning classifier will be thrown off. But the features out of this topological data analysis, they stay invariant. As promised, we actually trained 3 topological models. So the first one, we looked at these neighborhoods and we observed that for meaning carrying words or terms, they are way more dense than for words such as is or the, you might be able to make out on this picture. So we took a 6-dimensional descriptor of the density of this neighborhood, trained a model based on this. And then we applied what I showed on the earlier slide, it's called persistent homology, the mathematical tool which can find these circuits or holes in the data set. Out of this machinery, you get a persistence diagram. It's a certain fingerprint of the shape of the neighborhood. And then we use the numerical measure of magnitude of this diagram to train what we call the Wasserstein model. And our largest model used an even finer grained vectorization of this persistence diagram, where you build a kind of heat map of this fingerprint pointer scripture. And then after down projecting this with a convolution, we used it as input for yet another term extraction model. Okay, so this is my summary slide before I hand back to Renato. I listed these 3 different topological feature descriptors, and we trained a model independently on each of these. In the end, with the aim of just combining the predictions to increase recall on the term extraction task. And now we'll hear about our evaluation methods and what we got out of this.
Thank you very much, Ben. So we did 2 experiments. The first one was only conducted on the MultiWOZ dataset, where we trained each model on 4 domains in MultiWOZ and then evaluated on the 5th one. The reason why we only use 5 ones is that those are the only ones where you have single domain dialogues in MultiWOZ. The second experiment we call unseen ontology experiment. We train the model on each model on MultiWOZ and then evaluate on the much larger SGD data set. As you've seen before, it's at 4 times or around 3 times more domains and 2 times the dialogues compared to MultiWOZ. Another note is that we only train and evaluate on user utterances. The reason for that is that system utterances contain API calls, which we already consider structured. And we consider the union of the predictions because, as you will see, that the models trained on the different features, they tag a lot of different words on mainly on SGD. Which is why the combining the predictions is useful to get the best results. So let's first have a look at the leaf one house results. On this figure, you see the recall per left out domain. So the domain here we see at each of the corners is the domain we evaluated on, which was not seen during training. So when adding the predictions from the TDA feature and the MLM score models, the recall is already increased, which shows that even though the distribution of the data is similar to the training data, they still find different terms already. But the baseline still performs the best on the data because we think that really that the distributions are similar is that the reason why the language model is still able to basically show its strengths. So let's have a look at the unseen ontology results. So this is really where the models trained on the new proposed features show their strengths. As you see here, the TDA features, the models trained on the TDA features, almost double the recall on SGD, and the F1 score improves as well. Also, another interesting finding is that the certainty of the model trained on the persistent image vectors is the highest, which suggests that the properties captured in the topological features have such a general nature that they really help the models generalize to the unseen data and distinguish between the relevant and the irrelevant terms, although it has not seen them before. Now let's have a look at where or on which domains in SGD the models improve compared to the baseline. So one interesting thing we found is that although these mass language modeling scores come from the same model, the models trained on that still find terms from different domains. Especially, interesting is that it finds domains which were not seen on MultiWOZ, like banks and payment, which the baseline is really bad at. Also, the models trained on the TDA features basically find more terms in all of the 20 SGD domains. When looking at where the new terms come from compared to the baseline, it is again interesting that the M&M score finds a lot of new ones, although despite the low dimensionality compared to the Roberta embeddings, and also the TDA feature models show the greatest strength in generalizing. And of these TDA feature models, the persistence image models show the best performance here. So in this example, you can basically see why we consider the union of the predictions as this relation basically between the steakhouse the user wants and it being not costly is only found when combining all of the predictions from the different models. Here we see how some examples of the extracted terms on the SGD data. We see here that the false positives are mostly typos and partial matches, which maybe suggests some work on the evaluation. And also the false negatives are mostly long multi-word terms. This might be to because of the fact that maybe the contextual information isn't represented as well as in the language model yet with the TDA features. This is also what you can see on the average term length of every model. Yeah. So in conclusion, ontologies are really important for goal-oriented dialogue systems, but the manual construction really is a bottleneck for the variability of goal-oriented systems and the possibility of talking about other domains. And that's also, I think, part of some of the keynotes we've seen that the lack of data is really one of the bottlenecks for dialogue systems. So the language model features work quite well on the term extraction task, but the topological features really show the greatest strength for training general models, which are capable of being applied to a lot of domains. And also, this can be a first step maybe of automating some steps for ontology construction or for annotating data for other domains. And it also suggests to use topological data analysis maybe on all parts of dialogue systems, or at least for dialogue ontology construction. So these are the funders of our work. I thank you very much, and we are happy and looking forward to questions.
Thank you for the talk. My name is Patrick. I'm from Amazon. I was wondering, you said that for like the multi-word terms, these features may not perform as well. Now I'm wondering, that's probably because like when you create these point clouds, that they are centered around a single term. If you were to like build point clouds that like like if you first detect these multi-word terms and then build word clouds, either like spanning multiple words at the same time or combine these, would the same topological feature extraction still work, or is that kind of limited to like smaller areas in the space?
Yeah, so I think so the topological data analysis was based on sentence word embeddings. So I think maybe a direct application would be to maybe just embed like the more word terms with sentence word, and then do the topological data analysis on that. Or maybe
of course, you need to be careful that this doesn't blow up your computational cost. So theoretically, all these tools should work, even if you have multiple words and different patches in the space and you want to analyze this together. But unfortunately, the runtime is kind of exponential in the number of points. 50 is a good middle ground, and it depends on how fine-grained you want this analysis to be. So there's some trade-off. Yeah.
Okay, thank you.
Another question?
Thank you. This is Casey Kennington from Boise State University. This is really cool stuff. My question is about domain specificity. So the data you use had very specific, well-defined domains, and you can pull the ontology out of that. But if you still have to have data somewhere, so we have to give it text. What if it's more general? I imagine it's going to come up with a lot more false positives in that case and kind of invent that this is in a certain domain where it might not work. Is it in the plan to test it on a little bit more? I mean, you show that it generalizes, but I mean a domain that might span several different topics or domains at once. What are your thoughts?
Yeah, so the end goal is basically to apply this to unstructured data, so we don't have the label for, so like the general domains I think you're talking about, and basically use maybe basically bootstrap this approach that the training data is much smaller than the data you apply to. So I agree with you, and that's part of future work.
I got one question. So I know you said you're maximizing recall and not precision, but at what point is the precision will be too low that it's actually going to hurt the overall performance?
Yeah, I think maybe the point is that the F1 score still went up. I mean, basically when only the recall would have increased and the precision would have gone down so low that the F1 score would have suffered. I think that's basically when it's too low. So we show that we can increase the recall more than the precision would suffer. Like we're not just taking all the terms, right?
So I don't know if we said this, but these slot value pairs are used, for instance, in the dialog state tracker. Just to track all of these concepts. And now if you have to track 2 or 3 times as many as you would have expected, that's still fine, right? As long as there's not like a quadratic or exponential blow up. Okay.
Because normally, like the dialog state tracking complexity increases linearly with the number of terms which should be tracked.
If there's nothing else, I think our speakers again.